Hey, welcome back. This is Calc 1. Finally on to the fundamental theorem of calculus. Okay, so what this is going to do is kind of connect the antiderivative problem to the area problem. Okay, and it's a clever little thing how it works. So here we go. If f is continuous on the closed interval from a to b, and big F is the antiderivative of little f on this interval from a to b, then it turns out that the integral, the definite integral from a to b of f of x dx is equal to the difference of the antiderivative evaluated at the limits b and a. So it'll always be f of b minus f of a. Okay. Okay, so let me just show you the power of this. So for example, the integral from 0 to 1 of x dx. Okay. So to evaluate this, first we're going to need an antiderivative. So the antiderivative of x is x squared over 2. Okay. And then I'm going to evaluate that from 0 to 1 basically. So you plug in 1, so you get 1 squared over 2 is 1/2. Then plug in 0, so that would be f of 0. So you get 0 over 2, which is 0, and you get 1/2. So a lot quicker than all of this limit and finding weird sums, and a lot easier, right? Okay, so that's kind of the punchline. Okay, so why? How the heck are we allowed? Why? I don't get it, you know. So anyways, here's the proof. Okay, so let delta be a partition of our interval from a to b, designated by, as before, a equals x sub 0 less than x sub 1 less than x sub 2, all the way less than x sub n minus 1 less than x sub n, which equals b. And then make the following observation. And we're kind of going to back engineer the formula above for the definite integral. So we're gonna start on the other side, this f of b minus f of a side, and kind of work there, and eventually we'll be able to get over to the definite integral. Okay. Okay. So note. What is f of b minus f of a? Well, we can rewrite it as a sum of a bunch of things. In particular, f of b minus f of x sub n minus 1 plus f of x sub n minus 1 plus minus f of x sub n minus 2 plus f of x sub n minus 2 minus f of x sub n minus 3, so we're getting the picture, etc., all the way down to f of x sub, 2 minus f of x sub 1 plus f of x sub 1 minus f of x sub 0. Okay, okay, so all of that big long sum is equivalent to f of b minus f of a, because if you look at it, look, these guys will kind of cancel each other out. There's kind of like a telescoping effect where everything just cancels, and it just, you know, negative f of x1, positive f of x1, and you're just left with f of b minus f of a. X sub 0 is a, right? If you look at our partition, f of b is x sub n, a is x sub 0. Okay, so those are equivalent. Why do we care? We can we're trying to track down basically the Riemann integral in this nonsense. Okay. This thing is equal to, I'm trying to get the other color back. It will not come back for me. There you go. Okay. This is equal to a sum of f of something minus f of something. Okay. I equals 1 to n, so I need the I, the parent. This would be x sub I and x sub I minus 1. Okay. Then next I'm going to notice by the mean value theorem, this cool thing is true. So from our presumptions, f is continuous in the closed interval, and it has an antiderivative on this closed interval. So basically it's differentiable and continuous. So we can apply the mean value theorem to this function big F, is I guess what I'm trying to say. I'm sort of, it's always this issue for the mean value theorem. What did we need? We needed continuity on the closed interval and differentiability on the open interval. And right now I'm trying to apply the mean value theorem to big F. Okay, I want to apply MVT to big F. So what is big F? Big F is the antiderivative of F. In other words, the derivative of big F is equal to little f. In other words, they're saying that big F is differentiable on that closed interval. Okay. And also then on top of that, if you know something is differentiable, then it has to be continuous, right? So if diffie, then continuous. So I'm really worried that whether or not we can apply the mean value theorem to big F, but we can. Okay. So we can apply MVT to big F, and we note then there must exist C sub I in any one of these subintervals in the partition such that big F prime of C sub I is equal to f of x sub I minus f of x sub I minus 1 all over x sub I minus x sub I minus 1. Okay. So what? Why do I care? Well, it's because now I'm going to be able to rewrite the sum that I stopped with, this one I'm boxing in blue. I'm going to be able to rewrite that, and I'll almost get a Riemann sum out of it with this definition, or with this mean value theorem. Okay, so then we have, let's rewrite our that blue thing there, the sum of f of x sub I minus f of x sub I minus 1 from I equals 1 to n. We could rewrite that as a sum from I equals 1 to n of f of x sub I minus big F of x sub I minus 1 all over x sub I minus x sub I minus 1 times x sub I minus x sub I minus 1. Because you really haven't changed anything, you just multiplied n by x sub I minus x sub I minus 1 over x sub I minus x sub I minus 1, which is just equal to 1. So you haven't really changed anything there. But then you could take this big ugly thingamajig and turn it into just big F prime of C sub I. Okay, so it's the sum of I equals 1 to n of big F prime of C sub I. And you can this other thing is just some change in x, is our change in x sub I, right? That's by definition, that's just change in x sub I. And then the derivative of big F is just little f. So what we end up with is, lo and behold, the Riemann sum. So thus, through this kind of clever expansion of f of b minus f of a, we have that the sum from I equals 1 to n of f of c sub I times change in x sub I equals what we started with, which was f of b minus f of a. Then we could take the limit on both sides of this thing. Take limit as the partition goes to 0. So the limit as this partition goes to 0 of the sum from I equals 1 to n of f of c sub I, change in x sub I, which equals the limit of the partition going to 0 of f of b minus f of a. And we presumed that I guess f was, I think we presumed f was continuous, yeah. So f is continuous. This thing is going to be equal to, at least on the left, that thing is equal to the definite integral from a to the b of f of x dx. And then on the right, these are just two numbers, and the limit of numbers is just the numbers. You just get the constants right back, right? So this is just going to be equal to f of b minus f of a, and we got it. Yippee! Okay. So now, officially, we have connected the antiderivative to the area problem. Because that left side, we generally, up to this point in the past two sections, we've been treating it like the sum of a bunch of little rectangles. Okay, and then we take the limit as the number of rectangles goes to infinity. And basically, we're talking about, well, that can be set up, what is that? We could say it's area, right? We had not really connected that concept to the antiderivative, even though in the first section we were kind of saying that's where we're headed. But now here, conclusively, yes. The area problem and the antiderivative problem are connected. It's the fundamental theorem of calculus, guys. Okay, that'll connect these two facts. Okay, so let's take a look at doing some of these problems. And they're usually pretty easy, but the computations can be a bit nasty if you're dealing with fractions and stuff. Okay, so anyways, the first step is to get the antiderivative, which is what you're doing in section 5.1, right? And we sort of threw it to the side and studied the area problem, but now we're kind of back to the antiderivative again. So first thing, get the antiderivative. Okay, so integral of 7 is 7t, integral of 3t is 3t squared over 2. And then we need to, this thing right here is your big f of x. Okay? We need to evaluate that from a to b. In this case, a is -1 and b is 2. Don't make up your own notation, folks. If you do that, nobody's going to understand what the heck you're writing after a while. And this is standard notation, so don't, I've seen people do all kinds of weird stuff like put the bracket in front. I mean, I could read that, but it gets annoying when everybody starts inventing their own notation, and suddenly my job just becomes exponentially worse. So, I mean, I want you to be creative and think outside the box, but for the sake of communication, sometimes that makes it worse, being creative. So anyways, evaluate this at the end point. So first plug 2 into f of x. So I'll have 7 times 2 minus 3 times 2 squared is 4 all over 2 minus. And then you subtract away f of a. So you plug in -1 wherever you see t. So 7 times -1 minus 3 times -1 squared all over 2. Okay, so there we have it. This first part is f of b. That's this thing. And then minus this thing is f of a. Okay. And then you have to calculate, and this is the kind of the annoying part. It's real easy to make mistakes, but here it is. So this will end up being 12 over 2, which is 6, minus -7 minus 3 halves. So this will be 8 plus 7 plus 3 halves. So 15 plus 3 halves, which of course is 30 halves, plus 3 halves, which of course gives you 33 halves. Okay, so let's do another, and you're gonna do kabillions of these hopefully. Example 1 to 8 of the square root of 2 over x dx. Okay, so first things first, I'm going to kind of rewrite everything. So square root of 2 over square root of x, square root of 2 over x is the same as the square root of 2 over the square root of x. I can factor out the square root of 2. Get the integral of 1 over square root of x is the same as x to the -1/2 dx. and then integrate x to the negative 1/2 using power rule, add 1 to the old exponent. Negative 1/2 plus 1 is the same as negative 1/2 plus 2/2, which is the same as 1/2. Then divided by 1/2 is the same as multiplying by 2 over 1. And then I need to evaluate it from 1 to 8. Let's clean it up. So I have 2 root 2 times basically the square root of x. I'll just leave it as x to the 1/2 from 1 to 8. And then, so plug in 8 first. So I have 2 square root 2 times the square root of 8 minus, now you plug in 1. 2 square root 2 times 1. Okay. The square root of 8 is 2 root 2. Okay, so basically you have square root of 8 times square root of 8. It's just 8 minus 2 square root 2. And that's all she wrote for that one. Let's look at a trig version. Example, you have the integral from 0 to the pi of 2 plus cosine x dx. Okay, so first I can integrate 2 is 2x. Integral of cosine is sine. I need to evaluate that from 0 to the pi. So plug in pi first, so 2 times pi plus sine of pi minus, now plug in 0, so 2 times 0 plus sine of 0. And of course that'll equal 2 pi, sine of pi is 0, 2 times 0 is 0, sine of 0, that's always nice when all that stuff goes to 0. So you're just ending up with 2 times pi for your answer, okay? So it's pretty simple. Just find the antiderivative and then evaluate the antiderivative at the limits and take the difference. Okay. We also have this other, the second fundamental theorem of calculus, which talks about the derivative of the definite integral. Okay. And in order to get there, we need a couple of things. The first thing is the mean value theorem for integrals. Okay, and visually, the mean value theorem for integrals basically, what does it say? It says if you have a continuous function on a closed interval, you can find a value of c somewhere in this interval such that f of c, so maybe the c value is right here, so that you can kind of think of this region underneath the curve being equivalent to the area of that box I just drew. Okay, so the area, so if I'm going from A to B, the area underneath the curve given by f of x dx from A to B is equal to the area of that box, which is basically just b minus a times f of c. Okay, okay, so that's the mean value theorem for integrals. We can also from here gets what's called the average value function. Okay. So the average value function is just this integral rewritten. Basically, the average value of a function is going to be 1 over b minus a times the integral of f of x dx. And then we can always find some c value in the interval to give us that value if we just plug it into the original function. So here's some problems from the book. Find the value of c guaranteed by the mean value theorem for integrals. Okay. So in this problem, it's number 51. Or it used to be number 51. Well, I just have to put example now, sorry. Our function is f of x equals 5 minus 1 over x. And it's on the interval from 1 to 4, so we don't have any problems with continuity. And So what do we need? We need to find a c value such that f of c is f of c times b minus a, rather. Times, in this case, 4 minus 1 is equal to the integral from 1 to 4 of 5 minus 1 over x dx. Okay, so I need to kind of input c into the original function, so I have 5 minus 1 over c. 4 minus 1 is 3. On the other side, the antiderivative, I should put a c in there, not 3, into the original one. Sorry about that. It should be a c. On the other side, we have the integral, so it would be 5x minus the integral of 1 over x, if you remember, is ln absolute value of x, evaluated from 1 to 4. So here I have 15 minus 3 over c. On the other side, I have apparently 20 minus ln of 4. Absolute value of 4 is just 4, so I could write it ln 4 like that. Minus 5 times 1 minus ln of 1, which of course is just 0. And then I have 15 minus 3 over c equals, it'll end up being 20 minus 5, 15 minus ln of 4. 15's gone from both sides. Multiply both sides by -1. You get 3 over c equals ln 4. And then you can kind of cross multiply. C equals 3 all over ln 4. Okay. And I'm sure if you put that in your calculator, you'll find it's in between 1 and 4. Okay, find the average value. So average value comes up, I guess, in seems like it comes up in statistics. Find the average value over the given interval. So another example then. F of x equals 1 over 2x on the interval from 1 to 4. And so the average value formula, 1 over b minus a times the integral of f of x dx from a to b. So in our case, it'll be 1 all over 4 minus 1, which is 3, times the integral from 1 to 4 of 1 over 2x dx. Okay. So first I'm going to factor out 1/2. It'll give me 1/6 integral of 1 over x dx. And then you could find the antiderivative, 1/6, again, it's ln absolute value of x, evaluated from 1 to 4. And then you'll just have 1/6 ln 4 minus 1/6 ln of 1. Of course, the ln of 1 is 0, so you end up with ln of 4 over 6 as your average value. Okay, so anyways, the mean value theorem for integrals, or sorry, the mean value theorem for integrals, we have this, and we need it to prove the second fundamental theorem of calculus. The mean value theorem for integrals is proved in the book. You can go ahead and read that. But anyways, let's move on then to the second fundamental theorem of calculus. Okay. And so what this thing is going to do is kind of talk about the, I would think of it as kind of relating the derivative of an integral to the idea that they're kind of inverses of each other, right? So what's going to happen in the theorem, and we could actually write out, hey Dave, what is the theorem? So let me give that to you. Theorem 5.11. And it says that basically the derivative with respect to x of this integral, this definite integral from a to x of f of t dt is going to equal just f of x. Okay. We need, well, let me show you an example and then I'll go ahead and prove it. So, an example. Now, in these examples, you kind of think of the integral as a function, okay? In particular, it's finding the area from 0 to some variable x. And then you could figure out what it actually equals by putting in a number for x, and that'll be your function. Okay, so in this case, it's t times t squared plus 1 dt. Okay, so let's evaluate it, and then we'll get the derivative of it, and it should be, the derivative should be this part here inside. Okay. So anyways, let's evaluate it first. So I'll have I'll clean this t cubed plus t. I have to distribute before I can evaluate. That'll equal t to the 4th over 4 plus t squared over 2, evaluated from 0 to x. And then if you plug in x, you get x to the 4th all over 4 plus x squared all over 2 minus 0 to the 4th over 4, which is 0, plus 0 squared over 2, which is 0. So that second part will just be 0. And then if we take the derivative with respect to x, of big F of x, what do you end up with? Well, you get 4x cubed over 4 plus 2x squared over 2, which of course is the x cubed plus x, which is basically kind of what I was getting at. Okay, you just end up with what was originally on the inside. So the derivative of the integral just gives you back whatever was sitting on the inside of the integral. Okay, one way to kind of visualize what's going on here, again, you want to think of the integral as kind of a function. Okay, so this big f of x is finding the area from 0 to x. Okay? And visually, you could look at it as finding, this kind of region here to x. Right? Okay. To kind of find the derivative of big F of x, what you could do is kind of build that definition of the derivative. So if you remember, the definition of the derivative is basically like a slope, right? It's basically big F of x plus h minus big F of x, sort of, right? Anyways, let's just focus it all over at h, right? So the original definition is the limit as h goes to 0 of big F of x plus h minus f of x all over h, right? This is the derivative definition. It's f prime of x. So let's think about the bits and pieces here. So f of x is just the thing that finds the area from 0 to x, and that area here is shown visually. F of x plus h will find the area from 0 to x plus h, okay, which maybe is out a little bit farther. Then the difference between those two should just be this region right here. Okay. So what did I just say? The difference between f of x plus h and f of x should be pretty much just equal to the area of that yellow region. Okay, and if h is really, really super small, we can almost use a rectangle. We could say, okay, and it's just pretty much just this rectangle region here. So what is the area of that rectangle? Well, if this curve is given by some other function f of x, so big X is finding the area from 0 to x under, I guess I should say, little f of x. The difference between big F of x plus h minus f of x will be this approximately this little region, this rectangle. And what is that? Well, that's, height is f of x, and then the base is x plus h minus x, which is, of course, then f of x times h. And if you divide both sides by h, what do you get? Well, you get f of x plus h minus f of x all over h is pretty much f of x, approximately f of x. And what do you have on that other side there? Well, that's kind of like our derivative, right? That's the difference quotient. Okay. In other words, the derivative of this area thing is equal to this little f of x. And I don't know if that really helps, but I think I saw that explanation given to me by the Khan Academy guy. Maybe that's why I'm going. It was either the Khan Academy guy who explained it like this, or it was maybe a number files video I watched, or maybe it was even the 3 blue, 2 brown videos. I forget how. But those videos are made by a dude from Khan Academy, so it's all Khan Academy stuff. Anyways, hopefully that gives you some kind of intuition. I don't know what kind of intuition it gave you, but we got to prove this thing. Okay, sadly enough, yes, I have to prove the second fundamental theorem of calculus for you. Okay, so here it is. Basically, the derivative of the definite integral. The derivative and the definite integral kind of cancel each other out, but only when you think of the definite integral as this accumulation function. Okay, some function that gets area underneath the curve from 0 to x. Okay, so let's prove this thing. Proof. And I think we probably have continuity issues and stuff like that. But anyways, let's define. So first I define big F as this accumulation function. So big F of x equals the integral from a to x of f of t dt. Okay. By definition of the derivative, we have then this way of expressing f prime of x. So f prime of x will be f of well, it's a limit, right? So we need to include the limit piece. I can't just kind of wave my hands around that. It's the limit as change in x goes to 0. If you'd rather h goes to 0, of f of x plus change in x minus big F of x all over change in x. And inputting the integral parts into there, what is that? Well, that's the integral from a to x plus change in x of f of t dt, minus the integral from a to x of f of t dt. And what does that become? That just becomes that little wedge part that I was discussing above. Okay, that'll be that little area. Oh, hold on. Yeah, it's this wedge here, and what is that wedge here? That wedge is basically the integral from x to x plus h. Okay. Let's see if I can make that more clear. Well, you remember, and this is all over change in x, you remember the rule where you can always split up an integral. So if you have kind of an area going from, let's say, here's 0, and then, or even we could say from a, right? So they're using an a to x, and then x plus h is just a little, x plus, change in x is a little bit farther. It's basically the difference of two regions, right? So the first integral is this whole region from a to x plus change in x. The second integral is the smaller region from a to x. So when you take the difference between those two, you're left with just this wedge, right? This part of it. And what is that part of it? Well, you can rewrite it as an integral from x to x plus change in x. Okay, so hopefully I got you there. Change in x to 0. So that thing at the top is going to be the integral from x to x plus change in x of f of t dt all over change in x. Okay, so hopefully that makes some sense. There's other ways to think of it. But I think that'll work. Okay. Okay. So what else? Now I want to use that mean value theorem, right? So by the mean value theorem, there exists a c value in the interval from x to x plus change in x. Such that that integral in the numerator there can be replaced with f of c times the difference between the two endpoints of that interval. So we'll have this thing equaling change in x going to 0 of f of c times, so this should be x plus change in x minus x, which it will just be change in x, right? So this will just be change in x all over change in x, and then that simplifies, right, into just the limit of, so this equals the limit as change in x goes to 0 of f of c, okay? And then you can notice, we note here that c is in between x and x plus change in x, okay? So if you think about it, and this thing is continuous, we can evaluate the limit by kind of moving the limit inside the function, so long as that function exists at that value. We're thinking of the limit as change in x goes to 0 of c. So what is the limit of c as change in x goes to 0? Well, you could use a squeeze theorem, right? So note the limit as change in x goes to 0 of x is just equal to x. And then on the other side, the limit as change in x goes to 0 of x plus change in x, well, that's also equal to x as well. So if the two ends are equal to x, then the inner guy must be equal to x. So so what? Well, hence the limit of c as change in x goes to 0 must just be equal to x as well by squeeze. Okay, so at the end, then this thing just equals f of x, and we've proven what we set out to prove. Okay. So again, it's kind of an interesting proof. It's not any, you don't have to employ any weird high-powered techniques. I don't know. Okay, anyways, let's take a look at some examples then. So I'm sure the homework will want you to evaluate it and then show the fundamental theorem holds, the second fundamental theorem holds. Some books, they call this the first fundamental theorem, so there's some discrepancies against, some various people have various interpretations, I guess. Anyways, right, so the antiderivative of secant squared, of course, is tan. You want to evaluate it from pi over 4 to x. So you don't have to start at 0, I think maybe is the point of this one. So it seems like up here in my example, I started at 0 and went to x, but it could be any variable on the bottom limit. So you could use a. Anyways, tan, this will then equal, and this should be t. This will be equal to tan x minus tan of pi over 4 is just 1. And then if you take the derivative, we should get the secant squared right back, right? So the derivative, of course, of tan x is just secant squared x. And we've kind of shown it works. So in general, if somebody asks you to use, to find the derivative of an integral, a definite integral, so find f prime of x, and you're given that f of x is equal to this integral, like -2 to x of t squared minus 2t dt. To find that derivative, basically all you have to do is copy the guts with an x in it. Okay, so that would be x squared minus 2x. So it's pretty easy. Okay, how are they going to make it a little harder on you? Well, one thing they can do is change that upper limit. So for example, f of x equals the integral from 0 to sine x of the square root of t dt. Okay. This turns out to be kind of easy. All you have to do is a substitution and then use a chain rule. Okay, so you could say u is equal to sine x, and then also just keep in mind du with respect to dx is going to be equal to cosine x. Okay. So what's happening then, we want to find the derivative with respect to x of f of x. And so what we do is rewrite f of x as f of u, and then find the derivative of that with respect to u, and just multiply that by the derivative of u with respect to x. Okay, so let's do that. Right, so the derivative with respect to x of f of x is equal to the derivative with respect to u of f of u, and f of u is just the integral from 0 to u, so I replace sine x with u, of the square root of t, dt. But then I also have to remember to multiply on the derivative of u with respect to x. And so what do you get? Well, the derivative with respect to u of this integral will just give you back the square root of u, and then times the derivative of u with respect to x. So back subbing now, the u value was sine of x, and then the derivative of u with respect to x we found was cosine x. Okay. And that would be your answer. Okay, one last topic then, after all this high-powered theoretical material. It's kind of a physics thing, I suppose. So section 5 now, net change versus total distance traveled. Okay, so what is net change and total distance? And another word for net change is displacement. Okay, so imagine you're a quantum particle and you move maybe 3 units to the right, and then you move maybe 2 units backwards to the left, and then you move maybe 1 unit over to the back over to the right. The total distance traveled is the sum of all those movements. So it would be 3 plus 2 plus 1, so 6. Right. The net change, or the displacement, is just basically where you started, which would be over here, and then where you ended. Okay. So the distance from where you started to where you ended. So in our case, that looks like it's just 1, 2. And that's the difference between those two. So this is total distance, but the overall actual change, the net change or displacement, is just 2. Okay, and so the difference between these two when we're working with them is going to be like as such. The net change will be the integral of the absolute value. Sorry, the net change is just the regular integral. Okay, so it's the integral of the velocity function. Of course, you take the integral of velocity, you get back to position. So it would just be s of b minus s of a. So ending place minus beginning place. Okay. Then total distance traveled would be the integral of the absolute value of the velocity function. Okay. And what's that going to do? It's basically going to split your integral into a bunch of integrals, one for each kind of direction of movement. Okay, so let's take a look at one of these examples. They're giving us a velocity function is 5t minus 7, and they're saying over the interval from 0 to 3. And the easy part A is first find the displacement. So all you need to do is, and if you don't remember, position is s of t, but if you take the derivative of position, you're going to get back to the velocity. Okay, and then if you integrate velocity, you get back to the position. So if that wasn't clear, hopefully now it is clear. Okay, so anyways, displacement, all we're doing is integrating the velocity function over the interval from 0 to 3. So I need the antiderivative. And then I need to evaluate that. So first plug in 3. So I have 5 halves times 9 minus 7 times 3. And then minus that thing evaluated at 0. I think both those terms are 0. So you'll end up with 45 halves minus what would be 21, but multiplied to get a common denominator, that would be 42 halves, and that would equal 3 halves. So the total displacement 3 halves. For the total distance, that's a little bit more work. And it's because of the absolute value function. So the absolute value function represents a bunch of pieces. Okay, in particular, it'll be negative 5t minus 7 when 5t minus 7 is less than 0. In other words, when t is less than 7/5. Okay. And then it'll be positive 5t minus 7 when t is greater than or equal to 7/5. So when you see an absolute value function, you don't really know what you're integrating, technically. Yeah, I mean, it's this absolute value of 5t minus 7, but what is that? Well, it's negative 5t minus 7 in this interval and positive 5t minus 7 in another interval. And then you have to integrate those two guys. Okay, so it'll change it into this other integral, 0 to 7/5 of negative 5t plus 7 dt, and then plus the integral from 7/5 to 3 of 5t minus 7. Okay. Okay, it's even worse when you get like quadratic absolute values of quadratics, because then you have to do number lines and stuff like that and find out where it's positive and negative. Anyways, this guy, let's get the antiderivatives. Negative 5t squared over 2 plus 7t from 0 to 7/5, and this is a nightmare, plus 5t squared over 2 minus 7t from 7/5 to 3. So we substitute, so I have negative 5 halves times 7/5 squared, 49 25ths, plus 7 times 7/5 minus, well, that's nice, those will both be 0, and then plus 5 halves times 9 minus 21 minus 5 halves times 49 25ths. I need a little more room probably, minus 49 fifths. Ugh. Okay, so there's some doubles here. This term and this term are the same, so there's 2 of those. Let me clean it up first. 5 over 25 is the same as 1 over 5, so that'd be negative 49 halves, no, negative 49 tenths. I'm saying there's 2 of them. So negative 49 tenths plus negative 49 tenths is negative 49 tenths, which is negative 49 fifths. And then there's 2 of these characters. So that would be 49 fifths plus 49 fifths, which would just be 2 of those. So plus 98 fifths, I believe. And then the zeros are gone. And then we have a 45 halves, and then minus 21. Ugh. Okay, so this will be then, so what is 98 minus 49? 9, 49. So 49 fifths plus 45 halves minus, find a common denominator, 42 halves plus 49 fifths plus 3 halves, 49. So I need a common denominator, 490, no, 98 fifths, 98 tenths, sorry, plus 15 tenths. It'll be a miracle if I got this right. We'll find out. 13, 9, 10, 11 equals 113 over 10. Oh, I got it right. Holy tamales or something. 2. So they can make them harder, like I said. Let's see if I can find one. It's 4 point something. No, 5 point something. 5 point something. Let's see if they have anything more interesting. 5.4 maybe. Oh boy, what do they have for us? So they don't give me anything too bad. Actually, my first job interview, I was tutored online, and I was going to tutor algebra and calculus, and to verify that I knew how to tutor calculus, they gave me a problem just like this one. So great job to get if you're out of work as tutoring online. Okay, the higher your degree, the more you get paid. Unfortunately, for you guys, you want to get paid like somebody else, but it's an easy job to get, especially if you're kind of not a social butterfly, because you could apply for it online. At least you used to be able to back in the day. So this was a very easy job for me to get because I wasn't good at self-marketing. I didn't know anybody. I think like the only person I knew at the time was my mom. And my mom was like a preschool teacher, so she wasn't exactly going to plug me into the world of mathematics. So yeah. Then somebody said, "Hey, why don't you try teaching online?" And it was really easy to get that job. And I did my job interview over the phone, But they did give me this problem just like this one, and I had to figure it out. So how would I figure that out? Okay. You have to kind of figure out what. So our piecewise function this time, it's based off when the insides are negative, you have to apply a negative to it. When the insides are positive, you leave it positive. So I have to find out when it's negative, when it's positive. In order to pull that off, you could kind of do an inequality type analysis. So x squared minus 4x plus 3. You set it equal to 0 and solve to get your boundary points. Minus 3, x minus 1 equals 0. So x equals 3. X equals 1, then you have to do kind of a number line for the function. 1, 3, then you do your test values. 0, this is 2, x is 4, and this is for f of x. So when x is 0, that'll be negative times negative is positive, so greater than 0. When x is 2, again, negative times a positive negative, less than. When x is 4, positive positive is positive, greater than. So it's the piecewise version of this thing. Whenever you have a greater than, you just leave it alone. Okay, so x squared minus 4x plus 3 will be equal to x squared minus 4x plus 3 when we're in the interval from negative infinity to 1 or from 3 to infinity. And then it's negative x squared minus 4x plus 3 if you're in the interval from 1 to 3. Okay. So then you have to split up your integral accordingly for those. So you're going to go first from 0 to 1, and in that region you're using x squared minus 4x plus 3 dx. And then plus the integral from 1 to 3 of negative x squared plus 4x minus 3 dx. And then plus the integral from 3 to, what are we going to, 4 of x squared minus 4x plus 3 dx. Okay, so that's how you would set it up, and then you just have to find antiderivatives. 4x squared over 2, so 2x squared plus 3x 0 to 1 plus negative x squared cubed over 3 plus 2x squared minus 3x from 1 to 3 plus, again, x cubed over 3 minus 2x squared plus 3x from 3 to 4. And I'll leave the computations to you, but that's the idea. So I wouldn't be doing my job if I hadn't showed you how to do that, just in case you ever want to get a job as an online tutor, which I think is a really good job to get for somebody who's kind of not as social as the others. Okay, so you do have to deal with people, but to get the job itself, it's pretty easy compared to other jobs. Okay, so we'll leave it at that, and thank you for watching as usual, and we will see you next time.